All right, guys. I think it's already 3:30, and I will just begin the tutorial. Today uh, I'll give you a tutorial about how you can do the project. I'll start with the project menu so you can have a basic idea. Then probably I will show you how the pendulum work as well as the nonlinear um, model. So you can basically, I think this tutorial can give you a very basic idea about how you should design a controller. So as you can see from this menu, the pendulum consists of two parts. One is a rotatory arm, and the other one is inverted or the rod. So basically, I have a very simple model here. So that's basically the pendulum. That's the rotatory arm, and this is a rod. Uh, so let me see. So basically, this theta here represents the angle of the rotatory arm, and this alpha here represents the angle of the rod. And this is actually the non-linear model of the pendulum. So as you can see, this is basically the functions. So from these functions, you should derive the linearized state space model, which is actually the equations given here. So all you guys need to do is that you have to derive the linearized state space model, then design a controller. It can either be like LQR or pole placement to make sure that the controller can balance or stabilize the inverted pendulum. Uh, so for in order to do this lab, you have two options. One is that you can connect it connect to the connected to the remote desktop of CEI to the remote to the computers in CEI 2105 and do set everything up like this, or you can use the um, non-linear models given in on the course website and design the controller. So basically, these are the parameters of the pendulum of the state. These are the parameters for the inverted pendulum. So you need these parameters to derive the state space model of the pendulum. Uh, so I have the nonlinear model of the inverted pendulum here. So I will give you guys a basic idea how it works. Um, as you can see from this model, this one is a nonlinear model, and you can see one scope is actually monitoring the angle of the rotatory arm as well as the angle of the rod here. Let me zoom in for you guys. And when there is no input, it is not. So when there is no input or disturbance, um, okay. All right. So basically, at the inverted positions, the scope for this for this uh, sorry, I don't know why it's giving you this. So at inverted positions, the scope, the data, the reading of this alpha will be 0, which means the rod is at the inverted position, and the angle, the reading of this is theta can be anything. But when you give this rod any input, the rod will just like leave the inverted position, lost its balance, and then after several swing, it will finally stay at this position. So from the scope, sorry, my computer is just so slow. Um, yeah, so let's say if the angle of this theta is at the inverted position and no disturbance is given to the system, uh, basically the rod and the disk will stay at zero position, which means it is balanced. But if we give it the system a very small disturbance or any small input, the scope, the reading of the scope will be pi, either pi or negative pi, which means the rod is no longer at the inverted position, and it will finally sets at let me show you. So this is a case when there's no disturbance, there's no input. You can see that both the theta and alpha stays at zero, which means it's perfectly balanced, and the rod, and the rotatory arm is there is no movement of it. But when there is a small input, let's say we give it a very small initial condition, which we just it's like we push the rod a little bit. You can see that this blue line here represents the angle of the rod. It will just swing a little bit, then finally then finally stabilize at the uh, non-inverted position, which is pi. And this one represents the disk. So basically, that's basically the physical phenomena of this inverted pendulum. As I said, for this for this project, you are supposed to design a controller, which is here, to stabilize this inverted pendulum. I can show you guys how the controller works. All right, so once I connected this controller here, and remember we were having this before, the rod leaves the inverted position and finally moves to the non-inverted position. And if we have our controller here, Just sorry, it's running. It's just taking time. You don't need actually Quasar for this for project, but if you want, you can use Quasar Virtual Lab. But if you don't want to use Virtual Lab, you have to use the nonlinear model as I show here. You have to substitute the Quasar block width as well. So you guys can see, after the controller is implemented, the rod swings a little bit, then finally comes back to the inverted position, which is 0. So that's basically how the controller should work, and that's basically how you should observe from the scope. No matter what input you have for the system, your disk and rod should stay at this 0 position. And basically, if you are using Quasar software, this will give you the same. This will basically give you the same results from the scope. And meanwhile, this rod will always stay at this inverted position, no matter what kind of input you are having here. So basically, that's how the pendulum works, and that's how the controller, after implementing the controller, how the what is results you should obtain. And I'm not sure up to now Dr. Chen has give you the information how you should design the controller, because I think you guys might need to learn the observer as well. So if you are using the observer, this structure will change a little bit. You guys will having this output here, then go through an observer, then go to the controller here, then connect it to the negative feedback here. So I think that's pretty much the how you should design this project. First, you should derive as I said, you should derive the state space model. Okay, so you should derive the state space model. And these parameters here are for you guys to derive the state space model, because actually the pendulum works like this. This is a nonlinear system, but the controller you guys designed is a linear controller, which means the controller only works for a linear system. But since pendulum is a nonlinear system, the system model is linearized. This controller can only work in a certain, like a very small range. So in order to design the controller, you need this state space model, which is a linearized model to design the controller. Otherwise, there's no method. Like you guys haven't learned the method of designing a nonlinear controller. Is that clear for you, D? Okay. Yep. And is there any other question? controller, it doesn't have to be the state space controller, because you also have the option to derive the transfer function from the input, which is the voltage, to the output, which is the angle of the rod as well as the angle of the rotatory arm. So if you can derive the transfer functions, you can still use the method you guys have learned to design a phase lead or lag controller to stabilize this system. So it doesn't have to be the state space model, but I will suggest you guys to use state space because it's a multi-input, multi-output system, and state space is designed for multi-input, multi-output system. Yeah, is that clear? Yeah, maybe you guys need to use also need to use the an observer because actually the physical system of this pendulum here it will only give you these two angles, which is the angle of the rod as well as the angle of the rotatory arm. It will it will not give you these two output, which is the angular velocity of the rotatory arm and the rod. So when you do not have these two values, you need to design a controller to estimate all these four system states, then design the controller. That's why if Dr. Chen wants you guys to use an observer, first, okay, so first you should get this to output, then go through an observer, and then the output of the observer will um, then goes back to the feedback. I'm not sure so far because Dr. Chen will give you guys the designing details. So we are free to use it. Yeah, you guys are free to use a nonlinear model because the sponsor license might not work. Yeah. Yeah. So basic, it is very important for you guys to derive the linearized state space model because it will determine how your controller will be. Yeah. So uh, alpha and theta given. Yeah, I'm not sure whether you guys have learned the state space model, but yeah, from the output you can only obtain alpha and theta. Yeah, you need to use the state space model to find the other two values. Yes. If Dr. Chen probably Dr. I'm not sure so far yet, but if Dr. Chen says you guys can use full state feedback, which means you can get all these four datas. That's full state feedback because you can get all the states here, all the system states here. So if he allows you guys to design a controller with full state feedback, this structure will be good enough. Yeah. Yeah. So any other questions? Any confusing parts or okay. Yeah. Also, if you have any questions regarding to your assignments or lab uh, other labs, you may ask me or ask Stephanie here, the other
Yeah,
tutor.
any
She's over
doubts
here.
regarding the assignment, you can ask. They will be marked soon, I guess. Yeah.
Okay, so for lab one, I'm still marking it, and probably you guys will be getting the feedback soon. Uh, and I think today is a due date for lab two, so make sure you guys don't submit the lab two until the very last moment.
Any questions related to assignments?
So if you guys don't have any question, you can just leave, and we will be here until the last guy leave.